Okay. So, guys, force times time is equal to an impulse. So if we wanted to say impulse is I, is force times time. Impulse, all right, is force times time. And impulse, Ft, is equal to the change in momentum, delta P. And what is the equation for change in momentum? So it's the mass of the object times the change in velocity. Okay, so with all that being said, I know two things over here, mass and change in velocity. So I know delta V and mass. So what can I get? Momentum change, delta P. So what's 10 times negative 4? Negative 40. Okay, let's click. Bang. Okay, now look at the unit here. It's kilograms times meters per second. Why? Because mass is in kilograms and change in velocity is meters per second. And since I multiply those two, they're multiplying the units. Well, I don't know what the impulse is, though. So, Danny, what is my impulse going to be here? If this here is negative 40, what is my impulse? If impulse is equal to change in momentum. All right, so delta P is negative 40. And if in the equation, impulse is equal to that, it would be negative 40. And the only thing that changes is the unit. Now, the unit over here is Newton times seconds. And why is that? Because force times time is impulse. And
so it would be negative 40 kg times m/s?
For the momentum change. Okay, this is going to be the same value. Okay, well, how do I figure out what the force is, though? I equals F times T. And if I know what T is, right, so I would put negative 40 for I, and T is 0.01. So negative 40 divided by 0.01 is negative 4,000 newtons. All right, y'all see that? Okay, bet. So let's look at number 2. Number 2, we have an impulse here of negative 40. If impulse is equal to momentum change, what is my momentum change going to be? Negative 40. Yup. All right, the only thing that changed were the units. All right, well, look, if I know now what my momentum change is, if this is negative 40 and m is 10, what is my change in velocity going to be? Negative 4. You just put them in their spots, right? So negative 40 equals 10 times delta V, divide both sides, so negative 40 divided by 10 is negative 4 meters per second. Huh, wait a minute. So we have the same mass over here for 1 and 2, and the same change in speed. So what the hell is different? The time. Okay, so if this thing is acting on it for longer, what do we think is going to happen to the force? I think it's going to be larger. Okay, so if I is negative 40, if the impulse is negative 40 and the time is 0.1, now you would do negative 40 divided by 0.1, negative 400 newtons. So why is the force less? Why is because you have the same change in momentum. All right, so you're applying the same impulse in both 1 and 2, but one of them is happening much quicker than the other. Well, not much quicker, but it's roughly a factor of 10. So that's why the force is going to be 10 times less. So give me an example of a real life situation. Okay. How about if you were to just like step off a 6-inch little lift platform, all right, like a curb, big ass curb, 6 inches, and you were to kind of like just hop straight out, but then land. Would you land with your legs? Would you want to land with your legs straight, ankles straight, knees straight?
No, break
Yeah, why? This is directly related to this concept, to this physics problem. No matter what, right? So let's just say you're going to change your momentum from negative 40 kilogram meters per second down to 0, let's say. Well, you don't want to do it faster. Why?
Because I'm going to break your legs faster.
Because why?
Because the weight.
Because the force. So when you have the same change in momentum, all right, so the same impulse being applied, but if you do it over a shorter period of time, it requires a larger force. So you would be able to stop, right? That little jump from 6 inches, if you landed straight legged, all right, you'd be able to stop versus that little jump. And if you were able to like kind of bend your ankles, knees, hips, right, our body hinges at those points. Specifically, all right, well, not, that's not exactly why they're designed, but we're glad that they are because those kinds of movements help increase the time of the impact, which decreases the force. Cheerleaders, why do they practice on padded mats instead of like a hard wooden floor? Because they can injure themselves, which again has to do with this, all right? It has to do with the impulse. They got to change their momentum, right? Down to 0 either way. If they do a little 1, 2, I don't know, flippy, and then land, you'd rather them want to land on a mat than a hardwood floor. Why? Because the mat can increase the time of impact, even by, let's say, a couple hundredths of a second, like this, okay? Or this is 1/10 of a second, essentially, difference. And 4,000 newtons versus 400. That could be the difference between, all right, injuring yourself or being fine. So how does this really apply to us in the real world? Let's say in cars. How are cars designed using this concept? Give me a feature of a car that you think would help in this instance.
Safety features.
Safety features, yeah. Seatbelts. What about them? They're designed to kind of stop you, right, from using your inertia and flying you forward. But usually when you hit the brakes, right, quickly in your car, the seatbelt usually leans a little bit forward and then locks into place instead of instantly. Why? Because if it locked instantly and moved you forward, right, and you're still trying to move forward, it's stopping you very, very quickly. That's going to apply more force on you. So that's going to like probably hurt going across your shoulder, chest, whatever. So it gives like an inch or two and then locks so that it's extending the time, which decreases the overall force on your body. What else? What pops out of the steering wheel? Airbag. Airbag is not a completely solid thing. What happens is as it expands and hits your face or your face hits it, it kind of like starts to cave in a little bit. What is that doing? Again, increasing the time, which then decreases the force, which is better for your face. And then the material that the cars are made out of. So older cars are made out of like steel that were meant to kind of basically, if they get hit, not really mess up the whole frame of everything. Why is that not a good thing for your safety? Well, let's say you ran into a brick wall, right, with one of those older cars that are made of steel frames, it's going to stop you quicker. Again, same idea. The quicker you stop, the quicker you try and change your momentum, the more force is needed. Whereas the cars now, they're kind of designed to have like what they'll call crumple zones. So if they run into the wall, like the whole front end of the car kind of not accordions itself, but like, let's try to think of a word. Like an empty soda can. When you kind of like can start to squeeze it in and it crumples a little bit.
That's what it does.
Yeah. So the reason why cars do that is to extend the time of impact to decrease the overall force and limit, in serious injuries or deaths. So you may be like, oh my God, I wasn't even going that fast, but like my car is totaled because it crumpled so much. Well, guess what? it was maybe a different kind of car, okay, you could have been injured a lot more, and I think you'd be a little bit more pissed off that you may not be able to use your arm correctly anymore, or your legs may hopefully we're not talking serious deaths, but yeah, that's a potential of that. Okay, so impulse is a force acting on an object for a certain period of time in order to change the momentum. All right, and a change in momentum is caused by changing the speed depending on that force over a certain period of time. Okay, so then let's take a look at the impulse momentum concept builder, right, where we have the change table. So it's kind of like what we were just doing. So force times time, what does that give us? Force times time is our impulse. That's ugly force. That's ugly time. That equals that's an impulse, and it equals a change in momentum. Now, they're telling us our original momentum is 0 because the object's at rest. So when they ask for the final momentum, you're pretty much just going to have your whatever your change is here. Okay. So what's 18 times free? All right. So then what I can do here is, let's see, 54. If my impulse is 54, what did I change my momentum by? 54. They're the same. Now, if my initial momentum was 0 and I changed it by 54, it should be 54. Now let's see. Check answers. They should all light up green if they're correct. Great. Yeah, okay, I know. Yeah, buddy. Okay, what about the next one? What is 24 times 0.2 equal? 24 times 0.2 is 4.8, which means my change of momentum is going to be 4.8. And if I was originally at 0, boom. Okay, what about this one? Can I figure this one out? Well, if I was at rest and my change or my final momentum is 20, how much did I have to change by?
20.
Good. And if my change of momentum is 20, what does the impulse got to be? 20. Okay, so now I have my impulse. All right. If I wanted to write it like this, all right, I impulses force times time. Okay, so I have impulses 20, so if I had like a 20 under this equals 60 divided by t. I divide both sides by 60, so I would do 20 divided by 60, and that's, okay, it should be 0.0, or, yeah, no, 0.3 repeating. So let's see how we do that. 0.33, we'll call it that. Let's see. Yup. Bang. Okay, so you guys got that one. Now if we take a quick peek at this John here. Okay, so now an object is going to have an initial momentum. So that affects how we figure out what the final is. All right, so let's rock through this. Force times time gives me my impulse. All right, so what's 3 times 4? If I know that my impulse is 12, what does my change in momentum have to be? 12. Okay, so if I'm changing my momentum by a positive 12, and I was originally at 14, what would my final momentum be? What do you think we would do with this? Well, it wouldn't be 12 because we're not at rest anymore. Now our initial momentum is 14.
So do the same.
Would you divide it?
Wouldn't divide. So let's say I'm originally at 14, and I change it by a positive 12, which means I'm increasing it by 12. So what is my final going to be? 26. You add them together. All right, so let's just double check. Hit the check answer thingy. Okay. What about the next one? What do I do here? If I know what the impulse is, what is my change in momentum? 28. Okay, if I'm originally at 12 and I change it by a positive 28, what is my final momentum going to be? Good, 40, because we add them. If my impulse is 28 and the force is 8, to find time, I got to divide what? 28 divided by 8, and that should be 3.5. Let's check them. Oh, all right, solid. Let's see. Which one do we want to do? C, D, E. C. Okay. So if we know momentum, actually, you know what? I want to do D because I think D is a little bit of a more of a challenge. So all I know is time. I don't know impulse. I don't know force. I don't know change of momentum. I know the initial and the final. So what can I find? How can I find impulse?
34 minus
Good. So 34 minus 18, final minus initial, tells me how much I changed my momentum. So what is that number?
15.
Okay, so if I change that by 16, right, that's my change of momentum. Impulse is equal to change of momentum. So the impulse is then 16. And 16 divided by 0.5 will give me the force. So 16 divided by 0.5, 32. Hot dog. I don't know why I said hot dog, but regardless, okay, you guys are doing very good with this. I'm very happy with the participation. Okay, does anyone have any questions on this one? All right, real quick, I just want to see if you maybe let's take a quick look at what the hard one is. Most difficult relationships. Oh, silly. All right, so mass times initial velocity gives us our initial. So what's 4 times 12? So this dude should be 48. Now, if my impulse is 12, what is my change in momentum going to be? 12. So what is my final going to be? So if I change my initial by 12, what's 48 plus 12? 60. Dope. Okay, so now if I looked at this, right, if I had P is mv. So if I know that P here is 60 now, is equal to the mass doesn't change, 4, what is the new velocity going to be? So 60 divided by 4 should be how much? 15. Let's try it. Shwam. Oh, we got him. All right. All right. Guys are crushing this. Excellent job today. All right, so your homework assignment, I'm going to post, and then yeah, that'll be kind of on a wrap for us.